Dear students, I myself is Dr. Rajashekar Reddy, Assistant Professor of Mathematics, Government First Grade College, Pavagada. Now we discuss third semester BCA Mathematics. In this, we go for Unit 1 matrices. In the previous session, we learnt about eigenvalues and its characteristic equation. For any matrix is given, we write the characteristic equation and finding eigenvalues we learned. Now in this session we discuss eigenvectors. So already you know what is characteristic equation for any square matrix of order n and IB a unit matrix of order n, then the matrix polynomial is given by A minus lambda I. A minus lambda I given us the matrix polynomial. So what is characteristic equation? A minus lambda I into A minus lambda I is equals to 0 becomes the characteristic equation. The roots of the characteristic equation are called the characteristic values or roots or eigenvalues of the given square matrix. Now our task is to find eigenvectors. Let lambda be an eigenvalue of the square matrix A, then a non-zero column matrix X satisfying A minus lambda I into X is equals to 0, which gives Ax is equals to lambda X is called an eigenvector of A corresponding to lambda. So to measure the eigenvectors, we should use the condition Ax is equals to lambda X. So here we have proved that the constant term of the characteristic polynomial of a matrix is the determinant of A. So determinant of A is in characteristic polynomial only constant term. I can show this. Suppose A be a square matrix of order n. A be a square matrix of order n. If A be nth order square matrix, it contains n eigenvalues. You take that lambda 1, lambda 2 up to lambda n be its eigenvalues. What is the characteristic polynomial? A minus lambda I. So we prepare A minus lambda I, which is characteristic polynomial. Now expanding that characteristic polynomial A minus lambda I, we get that minus 1 whole to the power of n into c naught into lambda to the power of n plus c1 into lambda to the power of n minus 1 plus so on up to cn. In this one, by putting lambda is equals to 0, we get cn is equals to determinant of A. That's why the constant term of the polynomial, characteristic polynomial is equals to determinant of A. The second question is how that 0 is a eigenvalue of a square matrix if and only if the matrix is singular. To show this one, we take A be a square matrix of order n. So the eigenvalues are given by its characteristic equation, determinant of A minus lambda I is equals to 0. So put lambda is equals to 0 in this one, it becomes determinant of A is equals to 0. Determinant of A is 0, then A is singular matrix. So conversely, by assuming A is singular, determinant of A equals to 0. So that implies determinant of A minus lambda I is also 0. That implies determinant of A minus determinant of lambda I is equals to 0. Already A is singular, that's why determinant of A is 0 minus lambda into what is the determinant of identity matrix, unit matrix is 1. So 0 minus lambda is equals to 0. That implies lambda is equals to 0. Hence we say that 0 is an eigenvalue of the square matrix if and only if the matrix is singular. Like that, we find eigenvalues and eigenvectors. Suppose for the problem A is equals to -4, -6, 3, 5, we have to find the eigenvalues and eigenvectors. To measure the eigenvalues and eigenvectors, first we write the characteristic equation. What is the characteristic equation of any matrix A, any square matrix A is determinant of A minus lambda I is equals to 0. So for the matrix A -4, -6, 3, 5, characteristic equation is determinant of -4 minus lambda -6, second row 3, next element 5 minus lambda is equals to 0. On expanding this one, we get a quadratic equation of the form lambda square minus lambda minus 2 is equals to 0. On solving this, we get lambda values 2 comma minus 1. So these two are called eigenvalues of A. Now we have to find the eigenvectors of A corresponding to one of the eigenvalue lambda, such that Ax is equals to lambda x. So to find out the eigenvectors, you choose the condition Ax is equals to lambda x. That implies A means the given matrix -4, -6, 3, 5, and x is a column matrix x1, x2, that is equals to lambda, a scalar lambda, into x means the matrix, column matrix x1 comma x2. So on simplifying this one, we get that -4x1 -6x2 is equals to lambda x1, 3x1 plus 5x2 is equals to lambda x2. Now here we apply the eigenvalues. First, in the first case, you put lambda is equals to 2. You put lambda is equals to 2. Then the equation becomes -4x1 -6x2 is equals to 2x1. 3x1 plus 5x2 is equals to 2x2. On solving these equations, we get x1 plus x2 is equals to 0. Second one also same, we get x1 plus x2 is equals to 0. These equations are identically same. That means the system reduces to a single equation of the form x1 plus x2 is equals to 0. That means x1 is equals to minus x2. That is equals to, if you take k, then x1 is equals to k and x2 is equals to minus k. Hence, the eigenvector is given by a capital X is equals to a column matrix k, second row first element minus k. So we got one of the eigenvectors. Similarly, to find out another eigenvector, in the case 2, you put lambda is equals to another eigenvalue, that is -1. If you put -1 in the set of equations, we get 3x1 plus 6x2 is equals to 0. The second also same, 3x1 plus 6x2 is equals to 0. Solving these equations, we get x1 is equals to -2k, x2 is equals to k. So the eigenvector corresponding to lambda is equals to -1 is, it is a column matrix -2k, k. So like this, we can find out the eigenvectors. Similarly, for these problems also, eigenvalues and eigenvectors we can measure.